Alright, so when I would go to try direct substitution, what would happen here? I divide by 0. Can't do that, huh? Okay. Now, it's possible that there's an asymptote there, and if there was an asymptote, I couldn't evaluate the limit. Sometimes you're going to find you can't get rid of it. But when I try the dividing out technique or factoring, I do try to factor and see if I could get a factor to cancel. So can we factor the numerator?
Yeah.
What does that factor into? Okay. So this is like the same thing as evaluating this limit. Just rewriting it. And then this was something we did on the quick review and you've done on your summer assignment. What can I do? Okay. Now what happens when I substitute -3 in for x? Okay, what do I get? So I get that the limit is -5. So let's just take a look graphically so you can see what this looks like then. And it's hard to tell unless you zoom in. Doesn't look like it's undefined at -3, does it? But if I would type, if I would type in -3, do you see how it is undefined? Okay, and if I would zoom in, okay, there would just be nothing there on the graph. And so what it is just, it's a little hole. Do you see from the left and the right, though, that the function is going towards the same value, and that value is -5? Okay. All right. Second issue. Let's say I asked you to find the limit as x goes to 0 of the square root of x plus 1 minus 1 over x. Okay, once again, what would happen when you would plug in 0? The bottom is 0, it's undefined. Okay, so this technique, when it involves the square root, is we try doing something called rationalizing. And rationalizing would be a technique that we could possibly get that x to cancel out in the bottom. So here's how this technique works. You leave the square root expression the same, and you leave this expression the same, and you multiply by, we call it the conjugate. The conjugate means the sign in the middle is the opposite. And so to do that in this case, I would multiply by the square root of x plus 1 plus 1, and I would do that on numerator and denominator because we can multiply the top and the bottom of the fraction by the same thing. Now the whole point of this is what this is 100% of the time going to do is get rid of a square root. Okay, so you shouldn't be trying to do any messy multiplication here. What you should look at is this times this. What happens when we multiply a square root by itself? Yep, so the top, what we have is the top goes to x plus 1. Now hold on, what about the outers and the inners? Well, this would be a plus that expression and a minus that expression. So what should happen there? Because they're opposites, they're going to always cancel. And then -1 times 1 is -1. And I am now leave the bottom alone. Do not try to multiply it out. Okay? So I just leave it as x parentheses the square root of x plus 1 plus 1. So whatever one you're simplifying, simplify the one that you did, you picked for the conjugate, because that square root is going to cancel. The other one will not, but it will let us eliminate the discontinuity. Okay. So what does the top simplify to? X. And the bottom simplifies to x times the square root of x plus 1 plus 1. Do you see why I left the bottom alone? What can I do with those x's? Yep. So now I have left on top 1 over the square root of x plus 1 plus 1. Now put 0 in and see what happens. So yep, 0 plus 1 is 1, square root of 1 is 1. On the bottom I have a 2. This is a limit of 1/2. And once again, what you would see on the graph is it ends up being some kind of a square root function, but it just looks like a hole. You can see the values approach the same thing from both sides. At the end, if we have time, I should talk about factoring out certain cubed expressions, because we do not cover that factoring in Algebra 2. Once in a blue moon we see it. You guys will pick it up, no problem, but I'll put it on the board for you, the form for that. Alright, so those are our two techniques. The second thing that I want to talk about then, and have you write down in your notes, are two special limits. And the two special limits involve sine and cosine. And both of them, you have to just memorize them. You'll be expected to know them without the graph. Okay? Okay. So both of these things come from something called the squeeze or the sandwich theorem. Our textbook calls it the sandwich theorem because what you have, the sandwich, you have a function that is sandwiched between two other functions. It's like squeezed, so we call it the squeeze theorem in this book, same, because it's squeezed between two functions, okay? And here's what the squeeze theorem basically says. Well, later we have L'Hopital's rule, so, which is French. Okay. So if you have a function that is between two functions, and so the way I'm going to write that is h of x is less than or equal to f of x is less than or equal to g of x. So f of x basically is some kind of function that is squashed and it stays between this g of x and h of x. Okay? So if that is true in an open interval, containing C. C, if you notice so far, is the calculus general term for an x value. Okay. Okay, so let's say that's true. And let's say you know the limit of h of x. So limit as x goes to c of h of x, let's say equals some number. We're really not very creative. We'll call it L for limit. Let's say you also know that the limit as x goes to c of g of x is also L. This is kind of some common sense. Okay. So you know, here's g of x up here. Here's h of x down here, and you know f is where? In between. As we go to c, c is going to be over here. These two things are approaching the same thing. Tell me what I know then. It has to have the same limit, right? Okay. All right, so if that's true, then the limit, even if it's not defined at that point, even if we can't put in a number, then we know that as x goes to c, that function in between has the same limit. Some books call it sandwich because the term sandwich means, like I said, hey, you're sandwiched between two things, or squeeze, or some people call it the pinch theorem. It's basically these two functions are squeezing that other function to the same limit. So a picture of that would be, there's one in our book too, I'll tell you where, but here's this g function, the one I was talking about above, and here's h. And do you see how there's a dot there? Let's say I have no way of figuring out what f is at that value, but if I know these things, then I would know that as well. Okay. You guys might not remember this, but in pre-calculus, we actually used this concept when we were doing damped oscillation. Do you remember how we would have like an exponential function and a cosine and basically because the cosine was sandwiched between those two functions, it's going to approach the same value as those two functions. Okay. All right, so the two special trig limits that come from there, and if I have time I'll prove them, but they come from the sandwich theorem. One we saw in our lab, and that is the limit as x goes to 0 of sine of x over x. We cannot remove that x on the bottom, but it actually ends up being 1. All right. And the second one, here's the deal, guys. The second one is not as important. This is the most important one, the one you're going to see a lot. The limit as x goes to 0 of 1 minus cosine of x over x is the second one, and that is equal to 0. The proof for those two are on the bottom of page 65 in the Larson book if you want to take a look. But basically it's kind of the same thing. We use some trig manipulation, some trig properties to sandwich this function between two other functions that we know have a limit of 1. And it has to do with the fact that, do you remember how sines and cosines never get bigger than 1? That's what this one has to do with. Okay. Let's take a look at the graph and I'll see if you guys remember it. I'm going to put sine x over x in, okay? Okay, so see it comes up, comes down, but if I would try to put in 0, okay, if you would look at a table of values, these things approach 1. Let's do this. Gosh, it gets so close. Do you see that? So what does our calculator round it to? Yeah. It gets so close that it actually rounds it to 1. Okay. All right. What do you think would happen if I put a number in front? Let me do one example with this. Using this concept, can you try to evaluate what's the limit as x goes to 0 of, let's do sine of 4x over x. Like, just make some random guess. Okay. It is 4, but not for the reason you might think, okay? This works as long as these two things match. Do these two things match? No, because this is a what? 4x and a x. So here's what I'm going to try to do. I'm going to rewrite this as the limit as x goes to 0. I'm going to rewrite it as sine of 4x over 4x. Okay. And in order to do that, see how I just divided the function by 4, didn't I? What can I do to compensate for that? Okay. If I write 4 times sine 4x over 4x, what would happen to these? They would cancel, right? Okay. Remember what I said, as long as these two things are the same, the sine of something over that same something as x goes to 0 is always 1. So the limit of this is 1, but now what's in front? 4. So 4 times 1 would make that a limit of 4. So that's why it's a 4. I just showed you algebraically, but that's going to work for anything. Sine of 3x over x is also 3 and so on. Let's try one more. I know, Aiden, you're getting sleepy, aren't you? Okay. Let's try to use the sine x over x, okay? Let's try to do the limit as x goes to 0 of tan x over x. Okay. Can you try to rewrite this? How could you rewrite tan? See if you can rewrite tan in a minute. So I'm trying to get one of these so I can use this to do other things, okay? What's tangent? Okay, so this is like the limit as x goes to 0 of sine of x over cosine of x over x, correct? Okay, so now let's do some computation with fractions. This is the same as sine of x over cosine of x times what? Yeah. Okay. Are you okay with me doing some rearranging? I'm going to just rearrange the order. So I'm going to put sine of x over x over here. Are you okay with that? And I'm going to do 1 of cosine x over here. And I'm going to just kind of look at these things individually. Remember, this is the limit as x goes to 0. Give me your thoughts. We know that the limit as x goes to 0 of sine of x over x from above, that's where I'm saying you've got to memorize just that one, okay? That's 1. Very good. What about this guy? We couldn't put 0 there because we can't divide by 0, correct? But we can do that here because what's the cosine of 0? 1. You're right, it is also the secant, but we can evaluate it. So what's the cosine of 0? It's 1. 1 over 1 is 1. So this has a limit of 1 because it's one of our special ones. This has a limit of 1 because we can find it. So guess what the limit is? 1. And when you graph tan x over x, I'll show you that is the case. Look at when x goes to 0. Oh, you can't see. Do you see that as x goes to 0, that this is tan x over x, that it looks like it approaches 1?